Aluminium alloys are alloys in which aluminium is the predominant metal. The typical alloying elements are copper, magnesium, manganese, silicon, tin and zinc. There are two principal classifications, namely casting alloys and wrought alloys, both of which are further subdivided into the categories heat-treatable and non-heat-treatable. About 85% of aluminium is used for wrought products, for example rolled plate, foils and extrusions. Cast aluminium alloys yield cost-effective products due to the low melting point, although they generally have lower tensile strengths than wrought alloys. The most important cast aluminium alloy system is AlSi, where the high levels of silicon contribute to give good casting characteristics. Aluminium alloys are widely used in engineering structures and components where lightweight corrosion resistance is required. Alloys composed mostly of aluminium have been very important in aerospace manufacturing since the introduction of metal-skinned aircraft. Aluminium-magnesium alloys are both lighter than other aluminium alloys and much less flammable than alloys that contain a very high percentage of magnesium. Aluminium alloy surfaces will develop a white, protective layer of aluminium oxide if left unprotected by anodizing and/or correct painting procedures. In a wet environment, galvanic corrosion can occur when an aluminium alloy is placed in electrical contact with other metals with more positive corrosion potentials than aluminium, and an electrolyte is present that allows ion exchange, referred to as dissimilar metal corrosion. This process can occur as exfoliation or as intergranular corrosion. Aluminium alloys can be improperly heat-treated. This causes internal element separation, and the metal then corrodes from the inside out. Aluminium alloy compositions are registered with the Aluminium Association. Many organizations publish more specific standards for the manufacture of aluminium alloy, including the Society of Automotive Engineers Standards Organization, specifically its Aerospace Standards subgroups, and ASTM International, Engineering Use and Aluminium Alloys Properties. Overview: aluminium alloys with a wide range of properties are used in engineering structures. Alloy systems are classified by a number system or by names indicating their main alloying constituents. Selecting the right alloy for a given application entails considerations of its tensile strength, density, ductility, formability, workability, weldability, and corrosion resistance, to name a few. A brief historical overview of alloys and manufacturing technologies is given in Ref. Aluminium alloys are used extensively in aircraft due to the high strength-to-weight ratio. On the other hand, pure aluminium metal is much too soft for such uses, and it does not have the high tensile strength that is needed for airplanes and helicopters. Aluminium alloys versus types of steel. Aluminium alloys typically have an elastic modulus of about 70 gigapascals, which is about 1/3 of the elastic modulus of most kinds of steel and steel alloys. Therefore, for a given load, a component or unit made of an aluminium alloy will experience a greater deformation in the elastic regime than a steel part of identical size and shape. Though there are aluminium alloys with somewhat higher tensile strengths than the commonly used kinds of steel, simply replacing a steel part with an aluminium alloy might lead to problems. With completely new metal products, the design choices are often governed by the choice of manufacturing technology. Extrusions are particularly important in this regard owing to the ease with which aluminium alloys, particularly the AlMgC series, can be extruded to form complex profiles. In general, stiffer and lighter designs can be achieved with aluminium alloys than is feasible with steels. For instance, consider the bending of a thin-walled tube. The second moment of area is inversely related to the stress in the tube wall, i.e., stresses are lower for larger values. The second moment of area is proportional to the cube of the radius times the wall thickness. Thus, increasing the radius by 26% will lead to a halving of the wall stress. For this reason, bicycle frames made of aluminium alloys make use of larger tube diameters than steel or titanium in order to yield the desired stiffness and strength. In automotive engineering, cars made of aluminium alloys employ space frames made of extruded profiles to ensure rigidity. This represents a radical change from the common approach for current steel car design, which depend on the body shells for stiffness. Known as unibody design, aluminium alloys are widely used in automotive engines, particularly in cylinder blocks and crankcases due to the weight savings that are possible. Since aluminium alloys are susceptible to warping at elevated temperatures, the cooling system of such engines is critical. Manufacturing techniques and metallurgical advancements have also been instrumental for the successful application in automotive engines. In the 1960s, the aluminium cylinder heads of the Corvair earned a reputation for failure and stripping of threads, which is not seen in current aluminium cylinder heads. An important structural limitation of aluminium alloys is the lower fatigue strength compared to steel. In controlled laboratory conditions, steels display a fatigue limit, which is the stress amplitude below which no failures occur. The metal does not continue to weaken with extended stress cycles. Aluminium alloys do not have this lower fatigue limit and will continue to weaken with continued stress cycles. Aluminium alloys are therefore sparsely used in parts that require high fatigue strength in the high cycle regime. Heat sensitivity considerations. Often, the metal's sensitivity to heat must also be considered. Even a relatively routine workshop procedure involving heating is complicated by the fact that aluminium, unlike steel, will melt without first glowing red. Forming operations where a blowtorch is used can reverse or remove heat treating, therefore is not advised whatsoever. No visual signs reveal how the material is internally damaged. Much like welding heat-treated, high-strength link chain, all strength is now lost by heat of the torch. The chain is dangerous and must be discarded. Aluminium is subject to internal stresses and strains, sometimes years later, as is the tendency of improperly welded aluminium bicycle frames to gradually twist out of alignment from the stresses of the welding process. Thus, the aerospace industry avoids heat altogether by joining parts with rivets of like metal composition, other fasteners, or adhesives. Stresses in overheated aluminium can be relieved by heat treating the parts in an oven and gradually cooling it, in effect annealing the stresses. Yet these parts may still become distorted, so that heat treating of welded bicycle frames, for instance, can result in a significant fraction becoming misaligned. If the misalignment is not too severe, the cooled parts may be bent into alignment. Of course, if the frame is properly designed for rigidity, the bending will require enormous force. Aluminium's intolerance to high temperatures has not precluded its use in rocketry, even for use in constructing combustion chambers where gases can reach 3,500 K. The Agena upper stage engine used a regeneratively cooled aluminium design for some parts of the nozzle, including the thermally critical throat region. In fact, the extremely high thermal conductivity of aluminium prevented the throat from reaching the melting point even under massive heat flux, resulting in a reliable, lightweight component. Household wiring, because of its high conductivity and relatively low price compared with copper in the 1960s, aluminium was introduced at the time for household electrical wiring in North America, even though many fixtures had not been designed to accept aluminium wire. But the new use brought some problems. The greater coefficient of thermal expansion of aluminium causes the wire to expand and contract relative to the dissimilar metal screw connection, eventually loosening the connection. Pure aluminium has a tendency to creep under steady sustained pressure, again loosening the connection. Galvanic corrosion from the dissimilar metals increases the electrical resistance of the connection. All of this resulted in overheated and loose connections, and this in turn resulted in some fires. Builders then became wary of using the wire, and many jurisdictions outlawed its use in very small sizes in new construction. Yet newer fixtures eventually were introduced with connections designed to avoid loosening and overheating. At first they were marked AL-CU, but they now bear ACOALR coding. Another way to forestall a heating problem is to crimp the aluminium wire to a short pigtail of copper wire. A properly done high-pressure crimp by the proper tool is tight enough to reduce any thermal expansion of the aluminium. Today, new alloys, designs, and methods are used for aluminium wiring in combination with aluminium terminations. Alloy designations. Wrought and cast aluminium alloys use different identification systems. Wrought aluminium is identified with a 4-digit number which identifies the alloying elements. Cast aluminium alloys use a 4 to 5-digit number with a decimal point. The digit in the hundreds place indicates the alloying elements, while the digit after the decimal point indicates the form. Temper designation. The temper designation follows the cast to wrought designation number with a dash, a letter, and potentially a 1 to 3-digit number, e.g. 6061T6. The definitions for the tempers are F as fabricated, H strain hardened with or without thermal treatment, H1 strain hardened without thermal treatment, H2 strain hardened and partially annealed, H3 strain hardened and stabilized by low temperature heating. Second digit. A second digit denotes the degree of hardness. HX2 equals 1/4 hard, HX4 equals 1/2 hard, HX6 equals 3/4 hard, HX8 equals full hard, HX9 equals extra hard. O full soft. T heat treated to produce stable tempers. T1 cool from hot working and naturally aged. T2 cool from hot working, cold worked, and naturally aged. T3 solution heat treated and cold worked. T4 solution heat treated and naturally aged. T5 cool from hot working and artificially aged. T51 stress relieved by stretching. T510 no further straightening after stretching. T511 minor straightening after stretching. T52 stress relieved by thermal treatment. T6 solution heat treated and artificially aged. T7 solution heat treated and stabilized. T8 solution heat treated, cold worked, and artificially aged. T9 solution heat treated, artificially aged, and cold worked. T10 cool from hot working, cold worked, and artificially aged. W solution heat treated only. Note, W is a relatively soft intermediary designation that applies after heat treat and before aging is completed. The W condition can be extended at extremely low temperatures but not indefinitely, and depending on the material will typically last no longer than 15 minutes at ambient temperatures. Wrought alloys. The International Alloy Designation System is the most widely accepted naming scheme for wrought alloys. Each alloy is given a 4-digit number, where the first digit indicates the major alloying elements. The second, if different from 0, indicates a variation of the alloy, and the third and fourth digits identify the specific alloy in the series. For example, in alloy 3105, the number 3 indicates the alloy is in the manganese series. 1 indicates the first modification of alloy 3005, and finally 05 identifies it in the 3000 series. 1000 series are essentially pure aluminium with a minimum 99% aluminium content by weight and can be work hardened. 2000 series are alloyed with copper, can be precipitation hardened to strengths comparable to steel. Formerly referred to as duralumin, they were once the most common aerospace alloys, but were susceptible to stress corrosion cracking and are increasingly replaced by 7000 series in new designs. 3000 series are alloyed with manganese, and can be work hardened. 4000 series are alloyed with silicon. They are also known as alumin. 5000 series are alloyed with magnesium. 6000 series are alloyed with magnesium and silicon. They are easy to machine, are weldable, and can be precipitation hardened, but not to the high strengths that 2000 and 7000 can reach. 6061 alloy is one of the most commonly used general-purpose aluminium alloys. 7000 series are alloyed with zinc, and can be precipitation hardened to the highest strengths of any aluminium alloy. 8000 series are alloyed with other elements which are not covered by other series. Aluminium-lithium alloys are an example. Cast alloys. The Aluminium Association has adopted a nomenclature similar to that of wrought alloys. British Standard and DIN have different designations. In the AA system, the second 2 digits reveal the minimum percentage of aluminium, e.g., 150 X correspond to a minimum of 99.50% aluminium. The digit after the decimal point takes a value of 0 or 1, denoting casting and ingot respectively. The main alloying elements in the AA system are as follows: 1XX. X series a minimum 99% aluminium. 2XX. X series copper. 3XX. X series silicon, copper and/or magnesium. 4XX. X series silicon. 5XX. X series magnesium. 7XX. X series zinc. 8XX. X series tin. 9XX. X other elements. Named alloys: aluminium and aluminium iron alloy developed by Schneider, used for aircraft manufacture by Société pour la Construction d'Avions Métalliques Avameta. Alclad aluminium sheet formed from high-purity aluminium surface layers bonded to high-strength aluminium alloy core material. Burma Bright, a product of the Burma Metals Company, basically equivalent to 5251. Duralumin, Hindalum, product of Hindustan Aluminium Corporation Limited, made in 16 Gar rolled sheets for cookware. Pandalloy Pratt & Amp Whitney, proprietary alloy, supposedly having high strength and superior high temperature performance. Magnolium, Magnox, Salumin, Titanal, a product of Austria Metallag, commonly used in high-performance sports products, particularly snowboards and skis. Y-alloy, Hidaminium, RR alloys, pre-war nickel aluminium alloys, used in aerospace and engine pistons, for their ability to retain strength at elevated temperature. Applications: Aerospace alloys. Scandium aluminium. The addition of scandium to aluminium creates nanoscale Al3SC precipitates which limit the excessive grain growth that occurs in the heat-affected zone of welded aluminium components. This has two beneficial effects. The precipitated Al3SC forms smaller crystals than are formed in other aluminium alloys, and the width of precipitate-free zones that normally exist at the grain boundaries of age-hardenable aluminium alloys is reduced. Scandium is also a potent grain refiner in cast aluminium alloys, and atom-for-atom, the most potent strengthener in aluminium, both as a result of grain refinement and precipitation strengthening. However, titanium alloys, which are stronger but heavier, are cheaper and much more widely used. The main application of metallic scandium by weight is in aluminium scandium alloys for minor aerospace industry components. These alloys contain between 0.1% and 0.5% of scandium. They were used in the Russian military aircraft MiG-21 and MiG-29. Some items of sports equipment, which rely on high-performance materials, have been made with scandium aluminium alloys, including baseball bats, lacrosse sticks, as well as bicycle frames and components, and tent poles. U.S. gunmaker Smith & Wesson produces revolvers with frames composed of scandium alloy and cylinders of titanium. List of aerospace aluminium alloys. The following aluminium alloys are commonly used in aircraft and other aerospace structures: 7068 aluminium, 7075 aluminium, 6061 aluminium, 6063 aluminium, 2024 aluminium, 5052 aluminium, 7050 aluminium. Note that the term aircraft aluminium or aerospace aluminium usually refers to 7075. 6063 aluminium alloys are heat-treatable with moderately high strength, excellent corrosion resistance and good extrudability. They are regularly used as architectural and structural members. The following list of aluminium alloys are currently produced, but less widely used: 2090 aluminium, 2124 aluminium, 2195 aluminium. Al-The alloy, used in Space Shuttle superlightweight external tank, and the SpaceX Falcon 9 and Falcon 1E second-stage launch vehicles. 2219 aluminium. Al-Cu alloy, used in the original Space Shuttle standard weight external tank. 2324 aluminium, 5059 aluminium, used in experimental rocket cryogenic tanks. 6013 aluminium, 7050 aluminium, 7055 aluminium, 7150 aluminium, 7475 aluminium. Marine alloys. These alloys are used for boat building and shipbuilding, and other marine and saltwater sensitive shore applications. 5052 aluminium alloy, 5059 aluminium alloy, 5083 aluminium alloy, 5086 aluminium alloy, 6061 aluminium alloy, 6063 aluminium alloy, 4043, 5183, 6005A, 6082. Also used in marine constructions and offshore applications. Cycling alloys. These alloys are used for cycling frames and components. 2014 aluminium, 6061 aluminium, 6063 aluminium, 7005 aluminium, 7075 aluminium. Scandium Aluminium, Automotive Alloys, 6111 Aluminium and 2008 Aluminium alloy are extensively used for external automotive body panels, with 5083 and 5754 used for inner body panels. Hoods have been manufactured from 2036, 6016, and 6111 alloys. Truck and trailer body panels have used 5456 aluminum. Automobile frames often use 5182 aluminium or 5754 aluminium formed sheets, 6061 or 6063 extrusions. Wheels have been cast from a 356.0 aluminium or formed 5xxx sheet. Air and gas cylinders, 6061 aluminum and 6351 aluminium are widely used in breathing gas cylinders for scuba diving and SCBA.